Hello boys, hello girls, this is Mr. Klinkerman here, and I will be your virtual Algebra 2 teacher for those of you who decide to watch my video lessons to help you with your in-class lessons. Of course, if you're in my physical classroom, then I'm requiring you to watch these, so you don't have a choice. But I'm excited to have you here too, and I'm excited to have those of you that I do have in class. I think we're going to have a great year. You're going to learn a lot about Algebra 2. Starting with, in Chapter 1, some topics that are very familiar to you from your Algebra 1 days. And what we're going to start with in particular are real numbers and how you apply properties of real numbers. Two goals for this video will be these. One, that you will learn to classify real numbers, or really review it because you've done this before. I'm referring to integers, rational numbers, those types of things. Sound familiar? Good. And the second goal is that you're going to learn to order real numbers on a number line. Now we'll try to fly through this as much as possible because it ought to be something that's very familiar to you. But make sure you pay attention to the details. You ought to be taking notes every time you watch one of these videos. And you ought to be trying to investigate some ideas further on your own, whether it's trying extra examples that I give you or extra examples that your teacher gives you or that you can find online, whatever. All right, try some out on your own as well after you watch the video. Okay. So let's go on and let's learn about applying properties of real numbers and those two learning goals in particular. Starting with that goal where we're going to classify real numbers. Now, first of all, let's talk about what real numbers and their subsets are. And I'm going to put up a diagram here, and it's going to have a bunch of things that you're very familiar with. Okay? But I want to discuss what it means for a number to be a real number first, because most of you think, well, isn't everything a real number? I hope that you think that way. It's a little erroneous to think that way, but I hope that you think that way right now because every number that you've ever used in a course prior to Algebra 2 has been a real number. So I don't care if you're talking about the square root of 40, if you're talking about negative 10 zillion, if you're talking about the number 0.5, these are all real numbers. Okay? Now, why do we bother to specify something as a real number? Well, because there is such a thing as what are called imaginary numbers. They've never been relevant to another course that you've taken unless your teachers kind of taught you to go a little bit deeper, a little bit beyond what the normal curriculum requires in Algebra 1, for instance. But there are numbers that are called imaginary. We'll learn about them later on in this course, for sure. All right, so anyway, the set of numbers that you've learned up until now is called the real numbers, and that set can be divided into subsets with names that you're familiar with here. And I want you to pay attention to the arrows here because I'm trying to show you what is a subset of something else. All right? The natural numbers are a subset of the whole numbers, which are a subset of the integers and rational numbers, and those are all subsets of the real numbers. Okay? Irrational numbers have nothing to do with rationals or anything else. It makes sense that something can't be rational and irrational, I hope. Okay, got to be one or the other. But irrational numbers are still a subset of the real numbers. That's kind of the structure that we're looking at. Now, I'd like to go through and explain what makes something rational and what makes it irrational and all the rest of these subsets. And, well, that's kind of the point of this video, actually. So let's go ahead and take a look at some of that stuff. And we're going to first start by comparing rational numbers and irrational numbers with one another. And I'm going to go ahead and give you a definition that you ought to be familiar with for rational numbers. Okay? A rational number is any number that can be written in this form. P over Q. In other words, it could be any number that can be written as a fraction. With this little caveat, the numerator P and the denominator Q must be integers. Now I'm going a little bit out of order because I'm describing what integers are on the next slide, but let's just say that if you can write a number as a fraction and the numerator and denominator are decimal free and fraction free, then that number is a rational number. All right, so let me give you some examples of rational numbers. The simplest numbers that you can think of, such as the number 3, are rational numbers because you can write that as a ratio of two integers. That's another way of saying this. You could write 3 as a ratio of 3 over 1, or 6 over 2 if you like, or 12 over 4 if you like. All right, all of those are equivalent to 3. And since you can write the number 3 as a ratio between two integers, it is a rational number. Another example would be something like the square root of, say, 6.25. Now, at first, that doesn't look like it'd be a rational number if you kind of have an idea of what irrational numbers are anyway. But the square root of 6.25 is equal to exactly 2.5, and 2.5 is the same thing as 2.5, and 2.5 is the same thing as 5 over 2, isn't it? So you can, in the simplest form, write this number as a ratio between two integers. That makes it rational. I'll give you another example of a rational number here in a moment, but I think you've got the idea. And of course, anything that is not rational would be irrational, because that's literally what irrational means, is not rational, correct? So if I'm talking about an irrational number, I'm talking about a number that I cannot write as a fraction with the numerator and denominator both being integers. All right, now what kinds of numbers might fit that boat, you wonder? Well, how about something like pi, for instance? It's one of the most famous irrational numbers, probably the most famous irrational number. Now, a good rule, and one that's often slightly misunderstood, but a good rule for determining if a number is irrational is when you write it in decimal form, does the decimal go on forever or not? A little more to that. You happen to know that pi is 3.14159 and the decimal goes on forever, correct? Well, there's also no pattern to that, and that makes it irrational. If ever you look at a number in decimal form and its decimal goes on forever with no pattern, that's an irrational number. You cannot write it as a ratio of two integers. Pi fits that bill. Something else that would fit that bill that we can look at on your calculator, if you have that handy, would be something like the square root of 20, for instance. Okay? Now, the square root of 20 is not going to give you an integer. All right? Square root of 20 has to be between 4 and 5, right? Because the square root of 16 equals 4 and the square root of 25 equals 5. Well, type in the square root of 20 on your calculator and you'll get this for an approximation. Now, I just happened to write down the first 5 digits, but you get 4.4721, and you'll notice that it keeps on going. Your calculator can't display any further than the 10th digit for most of you, but nevertheless, it keeps on going, and you notice there's no pattern to the decimals. It's not like you have a 44444 or a 474747 pattern. Now, let's say you did have a decimal that went on forever, but it had a pattern, something like 10.45 repeating. That actually is a rational number. Ask me in class, I can show you how you write that as a fraction, because it is possible to take any repeating decimal and to write it as a fraction. That's beyond the scope of this video. But just know that repeating decimal patterns you can write as fractions. Those are rational. Okay, so you kind of get the idea of what an irrational number is versus a rational number. Great. Let's go on and talk now about whole numbers, integer numbers, and natural numbers. All right, and I'm going to show you part of the picture that I showed you earlier. You remember this from the diagram in a couple slides ago. And I'm trying to instill into you the subset-set relationship that we have going on here. I'm trying to show you that a natural number, any number that's a natural number, is also a whole number. The natural numbers are a subset of the whole numbers. And the whole numbers are a subset of the integers. Now, let's go ahead and talk about examples of each of these things. So we'll just start from the bottom and work our way up. You know that the natural numbers are the numbers that you count with, correct? So starting at the number 1, 2, 3, all the way up to infinity. Of course, infinity is not technically a number, but you get the idea. So 100,000, 2.34 million, those would all be natural numbers. Of course, that's 2,340,000, right? You could count to it. Now, a natural number is anything you can count to. You can't count nothing, so you have to start at 1. If you're counting things, you have to have at least 1 before you can count. So 0 is not a natural number, but when we're talking about the whole numbers, which you think of as numbers without decimals, you start at 0 there. And the whole numbers include 0 and every natural number. This is why I say the natural numbers are a subset of the whole numbers. Everything that is a natural number is also a whole number. Okay, so whole numbers, you know, do not have decimals. They do not have fractions. All right, and then every number that is a whole number also happens to be an integer. Now, when we're talking about integers, we're talking about the whole numbers and the opposites of the whole numbers. So you could still have 0, 1, 2, and 3, but you could also have -3, -2, -1, 0, 1, 2, 3. These are just some examples, right? You can keep going down forever or keep going up forever. As long as a number does not have a decimal or a fraction, whether it's negative or positive, it is an integer value. Now, quick note. Most people think that all negative numbers are integers because I make the distinction, or your teacher makes the distinction, that integer numbers can include negative values. However, when we were talking about the rational numbers a moment ago and the irrational numbers, well, negative pi is every bit as irrational, for instance, as pi is. So irrational numbers can be negative. Negative 10 over 3 is every bit as rational as positive 10 over 3 is. Okay, so negative numbers can go into a few different sets. Now let's take a look at an example. Let's forget that diagram, where you're going to have to figure out all the subsets of real numbers that numbers belong to. And let's look at these three numbers here: the square root of 24, 9.28, and 80 over 16. Now, my suggestion to you is this: if you have access, depending on your teacher, look at the decimal version of any square roots that you're given before you try to determine what number sets that belongs to. Now, say this is a square root of 25, for instance. Well, the square root of 25 would be equal to 5, and that would be a natural number, and thus it would be a whole number and an integer and rational, and, well, okay, we're only naming the subsets of real numbers, right? But the square root of 24 is not going to be a whole number. It's not going to be something like 2.5 like we saw earlier. It's going to be about this right here, 4.898979. Now, it looks like there's a little bit of a pattern here, but there's really not, because when it changes later on, that's a non-terminating decimal with no pattern, and that is always your indication that you have an irrational number, and that's the answer for that particular thing. That's the only subset of the real numbers that the square root of 24 belongs to. Okay, now how about 9.28? Well, first you always try to determine, is it rational or irrational? I went that route in part A without specifying it, but I determined it was irrational, right? Well, now I want to see, is this rational? By the way, isn't this clearly not a whole number or a natural number or an integer because it has a decimal part to it? But it's a terminating decimal. And anytime you have a terminating decimal, it's real easy to write that as a fraction, starting as a mixed number. This is 9 and 28 hundredths, correct? If you know your place value. So you could write that as 9 and 28 hundredths, which in simpler form is 9 and 7 over 25, right? Divide these both by 4. Simplify that. And then that becomes 232 over 5 if you go ahead and change this mixed number into an improper fraction. So the point being, that terminating decimal, I was able to write it as a fraction where the numerator and denominator were both integers. And so that makes this a rational number. And then if it's irrational, is it one of the subsets? Well, we already said since it has a decimal, it's not an integer, it's not rational. Sorry, it is rational, obviously. It's not an integer or whole or natural number. All right, now how about 80 over 16? You ought to recognize right off the bat that that's rational because it's already written as a ratio of two integers. 80 and 16 are both integers. But I always want you to think about these numbers in simplest form. And it turns out 16 goes evenly into 80, and it happens to go 5 times. So not only is this rational, but we can say it's a natural number as well. And if you remember that organizational chart where I showed you if something's a natural number, it's also a whole number, well, this is a whole number. And if something's a whole number, it's also an integer, well, this is an integer. So that number 80 over 16 happens to belong to all 4 of these subsets of the real numbers. All right, so now you ought to remember what the real numbers are and their subsets. Okay, last thing I wanted to talk to you about in this video was, how do you I'll get the hang of the software again. Hold up. There we go. Now I'm where I wanted to be. How do you order real numbers on a number line? Basically, how do you tell when one real number is bigger or smaller than another one, especially if they're real close to one another? All right, so we're going to graph these real numbers on a number line. Nothing tough whatsoever right here. Now, here's what I would suggest to you. And again, this is assuming you have a calculator, of course. And if you don't, then you just kind of have to wing it a little bit. It's not that difficult. Think about these numbers in decimal form when you're trying to think about where they would fit on the number line. All right. Now, negative 27/8 would happen to be negative 3 3/8, which if you tried, I just did that mentally, of course, but that's negative 3.375. Okay. The square root of 10, you know, is going to be between 3 and 4, right? Because it's between the square root of 9 and the square root of 16. We'll look at it as 3.162. Now, that's a non-terminating decimal. It's irrational. That's why we're learning to graph it, because it's one of those types of numbers we're learning, right? Irrational. If you weren't allowed to use your calculator, you'd just kind of have to use estimation techniques to figure out that was the approximate value. Now, negative 3.5, I'm going to write that as negative 3.500 so that it's easier to compare this number and this number that are really close in value. All right? And then, of course, pi is about 3.1415, so really about 3.142. And when I said I was going to write this as 3.500 over there, I did that so that this number and this number had the same number of decimal places. That's why they're easy to compare. And that's why I went to 3 decimal places for pi. Since I went to 3 decimal places for here, I can compare these two very easily now as well. All right. So we know what the approximate values are for each of these things. Now let's just place them on the number line. Let's start with the positive numbers. You know that 3.162 is greater than 3.142. Now they're both going to be between 3 and 4, and they're both going to be a lot closer to 3 than they are to 4. So let's say we put 3.142 or pi right there. And always when you label things on a number line, write it in the original form. We'll write that, label that as pi. And then just slightly past that is going to be the number 3.162, which, remember, we were supposed to label the square root of 10, so that's where the square root of 10 is. Square root of 10, a little bit larger than pi. Okay, and then for the two negative values that are really close to one another, remember that the larger the absolute value of the number is, the further to the left it goes on the negative number line if it's negative. So negative 3.500 would be further left than negative 3.375, which makes it the smaller one, by the way, doesn't it? Negative 3.5 is exactly in the middle, of course, between negative 3 and negative 4, so we'll say that's right there. Label it as negative 3.5, the way it originally was. And then negative 3.375 is going to be a little closer to negative 3 than that was. So maybe like right there. We'll label that in its original form, negative 27/8. All right, so from this video, you should recall now what the different types of subsets of the real numbers are, and you should know how to determine if a number is rational or irrational, and whether the rational numbers are wholes, integers, or naturals. And you ought to be able to place numbers on a number line from least to greatest, essentially. That's it. Simple skill. Thanks for your attention, guys. I know you will do well with this. Talk to you later.